I would like to welcome all of you to today's online seminar on interval methods in control engineering. And it's my pleasure to have with us today Nicolas Merlinge, who received his PhD degree from the Coventry University and Université Paris-Saclay in 2018. And he is currently a research scientist at ONERA, the French aerospace lab. And his main research interests are state estimation for nonlinear systems, system identification, and control for aerospace vehicles. And now we're looking forward to your presentation on set inversion and box contraction on Lie groups using interval analysis. Nicolas, the floor is yours.
Thank you. Thank you for the introduction. Before we begin, just a few words about my research interest. During my PhD, I studied the link between bounded probability kernels and interval analysis. And the concept was parameterizing bounded kernel supports with boxes using interval analysis. Since then, I've been part of the supervision team of several PhD students with my colleague Karim Daya, for example, and mostly based on particle filtering and Monte Carlo methods. In particular, we investigated state estimation on Lie groups, and Lie groups are very useful geometries for attitude estimation and navigation in general. So these works were mostly based on the Bayesian filtering field, but today's presentation is dedicated to my recent work on the following question. What can we do with interval analysis? Is it possible to use interval analysis on Lie groups in general? For example, perform attitude estimation for aerospace vehicles. To state the problem more precisely, I'm interested in performing set inversion and box contraction on Lie groups. So set inversion consists of finding all elements of an input domain X that satisfy constraints that f of x with f of function belong to an output domain y. So we also can see box contraction as a box hull, an interval hull of this solution set. And the two problems are quite related in that way. So they were successfully solved using interval analysis, and there is a huge literature about it, but for example, there is the well-known SIVIA method. There are many things about constraint satisfaction problem solving, and so here I give a reference with the Luc Jolin book that is very that explains many things about this, and there's a very huge literature about this, and it is still a very active domain of research, especially concerning dealing with non-linearities, and so it's something that is quite, there is a huge literature about it. But today's question is it possible to solve these problems where the variable explicitly belong to non-Euclidean manifolds? For example, if they are rotation matrices or something related to that. So if the f function inputs and outputs things that belong to non-Euclidean manifolds, and for example, Lie groups. In the literature, I see three ways to do things like that. For example, the first one is partitioning the manifold itself. So finding some way to partition the manifold with subsets that will behave like intervals or with the right properties we want. For example, being stable by intersection. The second way to do that is enclosing the manifold subsets we want to describe by superboxes or supersets that will belong to the Euclidean space that is around the manifold. So it's solving the problem in a higher dimension to have some Euclidean formulation. And the third way to do that is using some bijection between the manifold and the Euclidean space in order to perform classic interval analysis in the Euclidean space, but to parameterize some subsets in the manifold and to have a bijection between them. And that's more this kind of concept I will develop today. But let's just browse a bit the literature about this. Several research works were done using Lie group properties to perform interval analysis, and mostly taking advantage of symmetries and invariance in the Lie groups. For example, the first point in this slide concerns dynamical propagation of intervals using Lie symmetries. And it was done at Stabrotine. The two other points deal with set inversion and also box contraction for attitude estimation. And here, in the second point, they proposed a way to enclose some quaternion subsets in supersets that of 4 dimensions to describe some, to solve some attitude estimation problems. So it was done using SIVIA. Here you have some plots in yellow and blue of the solution sets in the quaternions, around the quaternion space. But there are 2 problems to that. First, the problem is solved in a higher dimension than the original problem and the manifold, because here it is solved in 4 dimensions, and the manifold is only 3 dimensions. So it's a bit more complex. And secondly, not all elements of the solution set belong to something that can be linked to the manifold. They don't belong, everyone don't belong to the manifold. So here, every point is not a valid or meaningful attitude. It's just an enclosure. That's why the same author proposed another way to parameterize that, and using a bijection between the quaternion space and Euler angles. So here in the solution set, everyone belongs to a rotation. Everyone represents the rotation in the solution set. And it's represented by Euler angles. But Euler angles also have their drawbacks. But here we have 2 examples of the 2 ways I've presented before: a superset around the manifold, or a bijection between the manifold and the Euclidean space, or a similar Euclidean parametrization of the Euclidean space. Another very interesting approach is the bisectable abstract domains that was developed to perform interval-like analysis in non-order sets or manifolds, for example, the complex plan. And it relies on the lattice structure concept that that makes it possible to define some elements that will behave like intervals, but when in a not order set. So it's an extension of interval analysis. And here we are more in the concept of partitioning the manifold in order to define subsets that will behave in the right way. And more generally, in the set membership estimation area in Lie groups, there are several works that were proposed. The first 2 points are different kinds of polytopes or zonotopes that will enclose some manifold elements in a superset. For example, with quaternions solved in a 4D space. So similarly as previously, but here with zonotopes. And the second work concerns rotation matrices. So it's there is a constrained polytope that will enclose some rotation matrix. So here we are more in the concept of enclosing the manifold elements in a superset. And the third point is quite interesting too, because it uses a bijection between the rotation matrices set. So it's basically it's a Lie group. It's SO3, the spatial orthogonal group, and it uses a bijection between this group and the Lie algebra. We will talk about it just later. But it uses a well-known properties of Lie groups, that is a bijection between the group and the Euclidean space, basically. And it allows the authors to define 3D ellipsoids in the algebra of the rotation matrices set to perform set membership estimation with some specific problem and specific measurement equation. But here we have the concept of bijection. It is quite interesting. And this bijection in Lie group in general is called the exponential mapping. We will talk about it in the presentation. And also I have to mention the works that were performed. Well, here it is not bounded estimation, but it's in the observer area and the Bayesian filtering area. That is also that there is an active research in that field about Lie groups, and it's just to mention that there is a huge literature in that area too. There are many contributions that, for example, brought Lie group Kalman filters, particle filters in Lie groups, and what is interesting is that the structures of the algorithm remain the same, but the formalism changed a bit, and there are other elements that need to be considered. For example, I give here an illustration of this with this table. On the left side, it is how to write Gaussian density in the Euclidean space. So it's a classic multivariate Gaussian density. And here is how we switch to Lie groups. It is the same structure, but there are some new elements. Here, for example, you have a log that appears, and in fact, it is just the reciprocal bijection of the exponential mapping between the group and the Euclidean space. So here we use the concept of bijection. And there are also other terms that appear that are linked to the curvature of the group. Well, so now if I want to define some interval or boxes on the Lie group, I need to define what could be an interval or a box formally, and then is it possible to do subpavings and to define inclusion functions in order to manipulate these elements. To begin, just a few words about the main Lie group property that I will use. It is the exponential mapping. So it is the bijection between the group and the Euclidean space. So the group is a differential manifold endowed with a group structure for its binary operation. And there is a bijection between the element of the group and the tangent plane at the identity element. And this tangent plane is called the Lie algebra. So there is a bijection between the group and an algebra. And what is very cool is that this algebra can be linked. It is isomorphic with the Euclidean space. So by composition, we can define some bijection between the group and RD. And so in the latter, in the presentation, when you will see X, it means that we take some elements of the Euclidean space from the Euclidean space and that we project them on the group. And when you see log, it means that we take some elements in the group and we bring them back to the Euclidean space. And the group, for example, can be the set of rotation matrices. Another important concept is how to define errors or differences, or how to compare two elements of the group. If I want to compare element A and element B belonging to the group J, I have two ways to do that. I will consider that in the binary operation is a product here, just generic product. So if I want to compare A and B, I have two ways to do that. I can multiply A by the inverse of B on the left side or on the right side, because in general, the groups are not commutative. So that's what we call the left or right convention for the side of the error. There are two ways to compare elements. Here I give an example with the group R plus, which is commutative. So in that case, it boils down to a trivial difference because the group is commutative. So here, comparing these two elements with left or right side, since we can commute, it is the same. It is a difference of the two elements. But it's not the case in general, and it's not the case, for example, for rotation matrices. Now that I can compare two elements in the group, I can bring back this difference inside the Euclidean space using the logarithm, the bijection we can then bring back this difference, and it's called the log Euclidean error. It is also called the exponential coordinate because it's the reciprocal bijection of exponential. So when you see log of something in the rest of the presentation, it means that we take some difference in the group and we bring it back to the Euclidean space. So based on this, I choose to define a Lie group box with two independent elements. The first one is what I call the origin mu, that is a point in the group. And the second one is what I call the algebra domain, that is just a classic interval or box in the Euclidean space. And I can define with these two elements a box in the group. So basically, if I can define some area around point mu x in the group, I can define the elements that are around this point in terms of log Euclidean error. So I can translate that in terms of some vector in the Euclidean space around 0. Because mu here translates to 0 because we are in terms of differences. And if I decide that this log Euclidean error belongs to a Euclidean box, then I can define some box that is equivalent in the group. So I can formalize that in that way, that a Lie group box is something that is made of the projection of the Euclidean box around the origin mu in the group. And I can write this on the left or right side convention because generally the group is not commutative. So here's an example with the set of complex numbers that have a unit modulus. The group is the unit circle in the complex plan. The algebra is the set of real numbers. The exponential is the complex exponential, and it is bijective in -p plus p. And the algebra is tangent at the identity element of that is 1 in the complex plan. And here you have an illustration of two boxes with their origin and their Lie algebra domain, so a classic interval in the real axis. And I don't call the origin a center. I would be tempted to call it a center of the box, but I don't call it a center because it's not necessarily at the center of the box or the interval. It can even be outside if we want. So that's why I call it an origin, because it's a point around which we will define the interval or the box. So based on this definition, we can define we can extend classic properties of Euclidean boxes to Lie group boxes. For example, the width of a box. I decide that the width of a Lie group box is the width of its algebra domain, because I wanted to preserve an invariance with respect to the position of the origin in the group. We can also define a volume in the Lie group by simply integrating a unit function inside the box, the Lie group box domain. But since it's not very convenient to manipulate, we can switch to the Euclidean space and with the exponential coordinates. And by substitution, we can get an integral that is in the Euclidean space on the Lie algebra domain. And here we have a term that appears that is linked to the curvature of the group. We can also define inclusion and intersection properties, and we can show that there is an equivalence between the inclusion in the Euclidean space and in the group, and same for the intersection, provided that the two boxes share the same origin in the group. And using this property, we can now define subpavings that are a finite union of boxes that cover a given domain without overlapping. And we can show that given a regular subpaving in the Euclidean space, and given an origin reference point in the group, we can project the Euclidean subpaving to the group, and we have a unique paving in the group from the Euclidean space for both left or right side convention. So it's pretty cool because it means that we can manipulate some paving in the Euclidean space, for example, with classic interval analysis, and we can project them in the group, and it is meaningful because there is a unique solution, provided that we have defined a side of the convention left or right for the definition of the boxes. Another key concept in interval analysis is the inclusion function concept. So we need that to perform set inversion, for example. Given a function f from one set to another, the inclusion function inputs a box x and outputs an interval L of all the output of f of x. So it is well known in classic interval analysis in the Euclidean space. I can define some inclusion function in groups if I want. So it's a box L in the group of all the outputs of the function inputting a Lie group box X. So I can define it, but it's not very convenient to manipulate. So using the exponential mapping, just using the definition of boxes, I can just replace X and the output of the inclusion function by the notation of the boxes with an origin in the groups and Euclidean box as a Lie algebra domain. And so it's just rewriting the equation 11, and provided that I choose an output origin in the output group of the function, I just have to express what is the algebra domain in terms of inclusion function, and I can define it as a Euclidean inclusion function that I call the equivalent Euclidean inclusion function, that is the Euclidean counterpart of the Lie group inclusion function. And I can define it using the bijection on the two groups, the input group J and the output group H. And I can express it in the left or in the right convention, depending on which side I choose to define my problem. So we can also show some properties of convergence. We have an equivalence between the convergence of the Euclidean equivalent inclusion function and the group function. And this allows us to manipulate Lie group boxes with functions that are in the Euclidean space. So basically, I started from a function from one Lie group to another Lie group. And thanks to the bijection, I translated into a Euclidean equivalent formulation that will be much more convenient to perform interval analysis. So now, with these elements, we are ready to tackle the set inversion problem on Lie groups. So I want to retrieve all elements of an input Lie group box that satisfy the constraint that f of x belongs to an output Lie group y. So both input or output are Lie group boxes. Since it's not very convenient to manipulate directly like that, we can use what we said before with the Euclidean equivalent formulation of the inclusion function, and this yields a Euclidean equivalent problem for this problem. So it is the same set, it is expressed in the group, but in terms here of the parameterization is changing. It is just in terms of exponential coordinates in the Euclidean space, using this function, this equivalent function in the Euclidean space. And then, provided that the output domain is full compact and that the inclusion function is convergent, we can show that it's possible to use the SIVIA method, for example, to solve the set inversion problem, and that the output is meaningful because it is unique in the group, and that it has a bounded volume in the group. So basically, the SIVIA method, it's well known, but I would just recall here, it outputs three subpavings. The internal subpaving that is guaranteed to contain all solutions, the output subpaving that is guaranteed to not contain any solution, and the undetermined subpaving that in blue here that may contain solution, and for example, it can contain the boundary of the solution set. And here there are two important points. Is that with the Lie group formalism, we can guarantee that every point of the solution has a unique counterpart in the Lie group, so it can be linked by bijection with the Lie group, and every point in the solution set here that is in the Euclidean space, that is isomorphic to the Lie algebra, everyone here represents a valid solution in the group. And we can also show that the volume of the undetermined subpaving, which is bounded in the Euclidean space, is also bounded in the group. So it makes sense to perform the bijection to retrieve group elements from that. And we can compute, it is equation 17, we can compute an upper bound for the volume of each box, each Lie group box belonging to the Lie group undetermined subpaving. That is the projection from the Euclidean undetermined subpaving of the SIVIA output. Then if we want to tackle box contraction, it is quite similar in terms of methodology, because we can start from the contraction problem in the group. So we want to find a box hull of the solution set of what I've defined as the set inversion problem. And we can define a Euclidean equivalent contractor that will be defined from the group, and we can define a Euclidean contractor in the Euclidean space that will contract the Lie algebra of the input box. and it will use the equivalent Euclidean function, and it is expressed as just a classic contractor in the Euclidean space. And we can show that if this Euclidean equivalent contractor has some properties, then we have the same properties for the Lie group, the whole Lie group contractor. For example, it is defined, these two conditions define the contractor, the contractance property and the correctness property. So we can show that the resulting Lie group contractor is also a valid contractor because it meets these properties. And in addition, we can show that if the contractor is the Euclidean contractor is monotonic or idempotent, then the Lie group contractor will have the same properties. So to summarize, what I've presented is a way to parameterize from a Lie group problem to express a problem in Lie group. So set inversion or box contraction problem inside Lie groups. We can translate it in terms of an equivalent Euclidean problem. We can solve it with classic interval analysis algorithms, and we can derive a solution that is meaningful in terms of uniqueness in the group and that has a bounded volume in the group. This work will appear pretty soon in a paper that have been accepted to the Automatica journal, and it will appear probably in a few days or weeks. So that's all for the theoretical part. Now I will illustrate that with test cases for attitude estimation. So we will use, as a group, we will use the spatial orthogonal group SO3 that represent the three-dimensional rotations and that can define state attitude for a drone or spacecraft to express the rotation between the Earth frame and the body frame. The Lie algebra of this group is the set of antisymmetric matrices, and it has 3 degrees of freedom, and it is isomorphic to the 3-dimensional Euclidean space, and we can define a 3-dimensional Euclidean vector that represents a rotation vector, and each term of this vector, each parameter is an angle. It is interesting to note that the exponential and logarithm mappings have closed form in this group. And now here's the first example that is just, I would call that a ball on the group. It is just provided some reference attitude in the group that I will call the state attitude matrix. We search for all attitude matrices that are close to this rotation matrix in terms of a norm and a threshold. And here we take the norm of the rotation vector, so it can be expressed in terms of logarithm of the error between the element we search for and the reference attitude. And by injecting the exponential coordinate, we can derive an equivalent Euclidean function that is just the square norm of the exponential coordinates. And it's identical in that case for left and right case, not because of commutation, because the group is not commutative, but because of the problem formulation. Now, if I inject this parameterization in SIVIA algorithm using the Kodak library, I got the left plot here. So these are the degrees of freedom in the Lie algebra, so in the Euclidean space, basically. And I have here the 3 subpavings. And I got, as a solution set, I got a ball whatever be the position of the reference attitude in the group, whatever be the attitude in the group, I always have a ball because of the problem formulation. And it's interesting to note that we are invariant with respect to the position in the group. However, it's not the case when I use another parametrization. So for example, the Euler angles here. And in the special case where we have an equivalent Euler angle with theta equals P out of 2, it is a well-known case of singularity for Euler angles. And here it is visually clear that we have an ambiguity between psi and phi. And instead of having a ball at this point of the rotation set, we have a tube. So this parametrization seems less representative because we have a tube instead of having a ball, and conceptually we would expect a ball to describe the attitude. So it's the first argument to use for this kind of cases the exponential coordinates and the Lie group frameworks instead of just Euler angles. Here is an illustration of what we get with the single box contraction with the forward-backward classic contractor. We start from the blue box, and the red box is the contracted box, and basically it is the box hull of the solution set of SIVIA. In order to assess more, I would say, more extensive performance of the algorithms for this test case, I've run some Monte Carlo simulations, and it allows us to compare the Lie group left formalism, the Lie group right formalism, and the Euler angle parametrization. And for the SIVIA output, here the criteria are the CPU time to compute, the volume of the undetermined subpadding, and the number of boxes that are necessary to describe the solution to the problem. And what we can see here is that the Lie group formalism yield better performance in terms of computational time and also in terms of representativity, because the volume of the indeterminate subpadding is thinner than with Euler angles, and they require less boxes to describe the problem. And for the single box contractor, here the Euler angle parametrization just doesn't converge. The criteria are the contraction rate between the input box and the contracted box, and also the lost space, the lost volume with respect to the box hull of a SIVIA output. It's just to see if we are minimal or not. And here we can see that the contractor is minimal for the Lie group formulation. Just for fun, here is a small variation of this problem, just by changing the function. If we want to use another norm, for example, here I use a squared Frobenius norm to compare the matrix, the rotation matrices. And then I can also derive an Euclidean equivalent function by injecting the exponential coordinates formulation. And still in right and left case, it's equivalent. And here it involves a cosinus. Visually, the outputs are quite similar to previously. And also the Monte Carlo results are quite similar in terms of performance. So it's nothing to add here. But a funny question is, what happens if we go outside the bijective domain of the exponential? Because outside the bijective domain, the exponential is only surjective. So here we encounter the effect of surjectivity when we go out of minus p plus p interval for the angles. And we see that we have some pattern repetition because of the surjectivity of the exponential. So it shows that we can go everywhere we want inside the bijective domain, but it's not representative if we go outside because we encounter the surjectivity effects. I note that the Euler angles suffer the same surjectivity effect because we have a pattern repetition here. So that's just to illustrate what happens if we go outside the hypothesis. Another test case here is a 3-axis magnetometer aboard a spacecraft. So here the function represents a measurement equation that will measure the local magnetic field in body frame. So here it involves a projection from the Earth frame to the body frame, and it is the attitude of the spacecraft. Still, I can derive an equivalent Euclidean formulation. In that case, it is not the same in the left or right error convention, so I have to treat them separately. And I have also to mention that in that special case, for implementation purpose, I had to use a second order Taylor expansion for the exponential mapping. So here are the SIVIA outputs in terms of Lie groups and Euler angles. In both cases, we get a tube because the problem is such that we fix 2 degrees of freedom, and there is 1 left degree of freedom alongside the magnetic field vector. So it's normal to get a tube in both cases. And here are the Monte Carlo results to assess the performances. And it's very interesting to note that here, left and right error formulation for the Lie group formalism are not equivalent. Here, the left, for this problem, the left side is better, it performs better. The right side is less performant, and the Euler angles is again even less performant. But it shows that left and right formulation are not equivalent. And what is funny is that for a single box contractor, the right side and the Euler angle are equivalent. So they are the Lie group formalism here is not doesn't help to do better than Euler angle in the right formulation. However, in the left formulation, it is still better. So that's interesting. That's important to note that there is no general case where it's Lie group are better in general, and that left or right side are equivalent or not. It depends on the problem and on the geometries of the problem. And it reminds us that nonlinear state estimation, and in particular in Lie groups, is also a matter of finding the best parametrization for a given problem, the more convenient geometry. And as said Henri Poincaré, a geometry cannot be more true than another. It can only be more convenient. So I'm not the first one to cite this sentence about Lie groups, but it's something that is important to keep in mind. So to conclude, I've presented a theoretical framework using the exponential mapping in Lie groups to deal with set inversion and box contraction when variables belong to Lie groups. I illustrated this for some rotation matrices estimation, and it seems to be an interesting parametrization for attitude estimation, at least in cases studied. Of course, many questions remain to be investigated because among them, how to deal with cases where the Euclidean box's uncertainty goes beyond the bijective domain of the exponential mapping. But in most application cases, I think it's okay to remain between minus p plus p. For example, in the Bayesian filtering area, it's an assumption that is quite always done, and it's okay to define uncertainty in such a domain. So I think that for many applications, it remains okay. but it's still a very interesting question, and I think there are many opportunities to improve that. And also, it could be interesting to test this framework in the dynamical propagation context in order to implement it in a complete state estimation algorithm with prediction and correction. Okay, thank you very much for your attention. If you have questions, do not hesitate.
Okay, many thanks, Nicolas, for your interesting presentation. And yes, I'm pretty sure there will be some questions. Who wants to start? Okay, Luc is the first one who has a question. You're still muted.
Okay, you can hear me, yeah? That's good.
Yep, now it's better.
Okay, so thank you very much for the presentation. I would like to know why the approach, how it can be generalized to a manifold. For instance, if I consider the sphere S2, probably you can provide some box maps of the sphere, since, for instance, it is homeomorph to a cube, and you can put 6 faces with 6 origins, and probably have 6 Cartesian boxes. And then you have some equivalence of the log and the exponential, but it's not a log and exponential because S2 is not a Lie group. And I have the feeling that probably your approach can be generalized to much more general manifold, which are not Lie groups. So, or maybe, can you confirm that you really need Lie group properties, or it can be generalized to other type of manifolds?
I think it can be generalized for other kind of manifolds, but for example, in Riemannian manifolds, you have also this kind of expand log bijection to local tangent planes, but it's more complex to my sense because they are only local. You have to redefine the bijection each time you move on the manifold. So I will just answer for why I choose Lie group here. It's because it was much more convenient, because we had in a wide bijective area in the group, and in many cases in the whole group we have we can define a log. So it was possible to have a global, not global, but quite wide bijection, and it was really practical to define boxes or sets that was compatible with applications. And in addition, since rotations and composition of translation and rotations can be expressed with Lie groups, that's why I choose to remain in Lie groups. But you're right, I think it is possible, since we use the concept of bijection, and it is mostly this is the most important concept here. I think it can be extended to other manifolds. Yes, and for example, the sphere, I think it's possible. Yes.
Yeah. And I have another question also. So you probably have to cover your Lie group with some kind of boxes. So I would say that in SO3, for instance, you need how many origins do you need, and how many boxes do you have, and do you think that these boxes may overlap, or they have to have no intersection?
You mean by defining a padding?
Yes, when you want to find a global padding of your Lie group, then probably you need different origins. You need more than one origin and more than one Cartesian box, because you have to cover your Lie group.
You want to cover the whole SO3 group?
Yes, yes.
Okay. In that case, I would say I've not thought in that way, to be honest. I'm not sure to be able to answer to be sure that we will have a joint covering. But I think by bijection, since we have a bijection that extends to minus p plus p in the algebra, I think that by defining a paving in the algebra on the whole bijective domain, normally we could we can retro project it on the group, and we should have a meaningful paving.
Okay. Okay. Thank you very much for your answer.
The overlapping question is very interesting because it's I show in the paper that well, it's possible when you have a unique origin, you can map the paving in the algebra with the Lie group paving when you have a unique origin for all boxes. But because of the curvature and the non-commutativity in the general case for Lie groups, it's complex to have paving with different origins, and it's not impossible, but we have to be very careful to not having overlapping, because we will have distortions because of the curvature. So it's linked to the Baker-Campbell-Hall, the BCH, Baker-Campbell-Hausdorff formula that has several approximations, and with some approximation we can have a first order approximation that is quite interesting to see what could happen in terms of distortions.
Thank you.
Hey, do we have any further question? If not, I have two of them. The first one is what I think was really impressive at the end is the comparison of computing times. Could you give us a little bit of insight how you implemented the SIVIA approach? Is it just state-of-the-art C++ implementation, or did you make any tricks concerning parallelization or anything else?
No, I just used the SIVIA output implemented in Kodak, and the Kodak library implements some part of the IBEX library. And as far as I know, in the documentation, what I've understood is that the SIVIA version of the Kodak library is the same as the IBEX, so it's basic C++, and I didn't change anything to that because I wanted here to stay as naive as possible in terms of methodology. I didn't want to change something to optimize or something. I just wanted to test the differences between the different parameterization. I wanted to assess the soundness of my theoretical formulation with classic tools. So that I used the state-of-the-art SIVIA and the state-of-the-art forward-backward contractors. But I'm pretty sure that it could be optimized with more advanced contractors and algorithms. And you probably know far better than me the different ways of doing that, I'm pretty sure. But here I wanted to remain as close as the basic state of the art, because what I wanted to assess is the importance of the way of parameterizing the problem in Lie groups.
Okay, this directly raises a second question. If you would like to propagate, for example, your sets that you have identified here also over time,
yeah.
do you plan for future work to embed your approach, for example, also in the solution of differential equations?
Yes.
Because then this would be really nice, something like a predictor corrector state estimation that you get at the end.
Yeah, I'm thinking about it. And it's not very simple because of the group curvature. We have to be very careful. And but that's not the only one, but it's linked to the reason why I choose an independent parameter, two elements that are independent: the origin and the Euclidean algebra domain. Well, the Euclidean domain, that is so-called the algebra domain, because if we remove 1 degree of freedom, if we fix, for example, the origin at the center of the interval or something like that, it's very dangerous because of the curvature. I said before, it is linked to the BCH formulations, which means that the logarithm of the product of exponential is not, in the general case, it's not the sum of the logarithm when we are not commutative. So we have to be very careful with that. And I think it's possible thanks to that, it's possible to extend to dynamical propagation.
So I think you're right with this problem that you just described, and I think there may be also a second one that comes into play. If you're propagating your boxes, you definitely have to restart bisectioning then at a further time step. And maybe then also, in order to limit the complexity, you would need something like a merging strategy. And I think this will then again suffer from the problem that you just mentioned, corresponding to this curvature problem.
Yeah.
Okay, and then I have a final question. The final one is what you did at the moment. You just worked with in the interval domain with the axis-aligned boxes.
I'm sorry, I didn't get your last sentence.
Yes, the bisectioning has been performed on intervals with the axis-aligned boxes.
Yes.
Is there a way to replace the interval boxes, in this case, for example, by sonotopes, if you want to represent some dependencies that you know due to some further physical insight?
Yes, I think so, yes. Because
would it be the application then of the works you quoted, for example, I think you quoted Brenner's paper somewhere at the state of the art.
Yeah.
At the beginning.
I'm not sure I get you talking about.
Yes, you have the #1 here. There's a paper of Brenner, Rego, and
yeah, that's something I'm thinking about. I think it's more convenient to work inside the manifold via the bijection rather than enclosing the manifold here. So I think it's much more convenient, yes. And I think it can, since we can define intervals, we can also define other kind of domains. And that was done previously with the ellipsoids. They define ellipsoids in the algebra, directly in the algebra. And so ellipsoid axis were the axis of the vector space of the algebra. And I think I believe more in this kind of approach.
Yeah, okay.
It's just a matter of parametrizing. It's just a matter of geometry. And
yeah, I think everything you refer to this quote that you had given at the end of your presentation, find the suitable parameterization that is yes, well adapted to the problem that you really want to solve at the end.
Yeah, and the sentence by Henri Poincaré is very important, I think.
Okay, now let's have a look again at the list of participants. Is there anyone else who wants to ask a question? So if not, yeah, we have the perfect slide now. Now again, thank you also, Nicolas, for your presentation. Thanks to all the participants who attended today's presentation. And yes, we'll see each other soon in the next seminar. And please keep in mind that we have switched to Monday mornings now, at least till the end, until the summer break. Okay, then have a nice week and see you soon.
Thank you very much.
Thank you.
Thank you for the invitation, and thank you for your attention.